Welcome everyone to this next lecture on machine learning for core engineering disciplines, and we have begun a journey with a discussion of probability and statistics. We dealt with frequentist and Bayesian statistics, then we looked at Bayes' theorem, and finally we came to the concept of continuous and discrete random variables. We also looked at things like the probability density function and the cumulative distribution function. So in today's lecture what we will do is we will get started with a way to convert from one distribution to another, right, one probability distribution function to another, which is often useful, and then we will switch gears and then we will start talking about sample and population properties which are useful to quantify the characteristics of a certain distribution. So let us get started. So the first thing that we are going to look at is the conversion of random variables to other distributions. Okay, so that is what we are going to look at, and like I was saying, this is useful because programming languages only have inbuilt functions for specific probability distributions. Meaning that you can only generate random numbers that are sampled from certain specific probability distributions, for example say a uniform distribution or a normal distribution. But what if you want to generate a random variable that is sampled from an exponential distribution, right, or from the student's t distribution? How do you do that? That is what we will learn here, right. So in this scenario, right, we can use variable transformations to obtain random numbers following the desired distribution, right. So in this scenario variable transformations can be used to convert, right, random variables sampled from a certain distribution to those sampled from another distribution. Right, and I already gave you an example, right. Your computer for example only has a random number, right, that is sampled from the uniform distribution between 0 and 1. How do you convert this to a random variable y, right, that is sampled from the exponential distribution with a parameter lambda, right. So is there a function which relates y to x? That is what we are going to learn here, right, and as you can imagine this is quite important because yeah, you only have functions, right, that can sample from certain specific distributions. Okay. So I will tell you how to do this. The derivation of these equations are beyond the scope of this course, and you can refer to any standard textbook on probability and statistics to learn the derivation of the equation that I will be presenting, right. So given a random variable x, given a random variable x, with a probability density function f of x and a cumulative distribution function CDF capital F of x right. Let y equals r of x and g of y denote the PDF of y and capital G of y denote the cumulative distribution function of y, right. So, essentially we are postulating that there is a function y, right, function r, right, which can convert the random variable x to a random variable y, and then y will have the desired distribution that we want. Okay. So, this conversion depends on the inverse of the function r, right. So, you know that given any function r, right, you can find the inverse of that function, right. So, let r inverse y denote the inverse of r of x. Okay. So, now we are in a position to explain how we can convert the random variable x to the random variable y. Okay. So, if r inverse is an increasing function, okay, and I hope you know what I mean when I say an increasing function. It is a function whose value increases as the argument of the function increases, then in that case your capital G of y is given simply as capital F of r inverse y, and if instead of the cumulative distribution function, if you want to work with the probability density function, then small g of y will be given as f of r inverse y times d dy of r inverse y. Okay. So, what this means is, if you know, right, the function r that relates the random variable x to the random variable y, then you can obtain the CDF of y from the CDF of x, which is capital F, and you can obtain the PDF of y, which is small g, from the PDF of x, which is small f, right. And this requires knowledge of the inverse function, right. So, this is quite straightforward if you know the meanings of these concepts, and like I said, if you feel that you need more time to absorb this, you are free to refer to any probability and statistics textbook. Now, moving forward, if r inverse instead of an increasing function, if it is a decreasing function, okay, then there is a small change in how you can find out the CDF and the PDF. In this case, the cumulative distribution function, the CDF g of y is 1 minus f of r inverse y, and the probability density function PDF is small g of y is minus f of r inverse y times d dy of r inverse y. Okay. So, again we see that there is a prescription to convert, right, the cumulative distribution function of x to the cumulative distribution function of y, and the probability density function of x to the probability density function of y, and all that you need to know is this function r inverse y, which is the inverse of the function that converts x to y, right. So, if r is the function that converts x to y, then r inverse is the function that converts y to x, right. So, I hope this is clear, and we are going to take up an example which will further solidify what we have just learnt. Okay, so let us go ahead. Okay, so let us take up an example, right. Before I do that, I mean, I just want to be cognizant of the fact that not everyone may be aware of inverse functions. So, I just want to give you some examples of pairs of inverse functions. Of course, most of you may already know this. So, if r of x is e to the x, then you know that r inverse of x is basically log of x, right. Why? Because if you operated r inverse on r of x, basically you would be doing log of exponential of x and you will get back x, right. So, that is why a log of x is the inverse of e to the x. And another example is if r of x is sine of x, then r inverse of x is basically sine inverse x, right, that is how we denote it. And we know that then r inverse of r of x would be sine inverse of sine of x, which will simply be x, right. So, this is what is meant by inverse functions. So, hope that is clear, right. So, now let us take the real example that we wanted to consider of conversion from one type of a random variable to another type of a random variable, right. So, in this example, right, we are tasked with the following: let x be a uniformly distributed random number in the interval 0 to 1. We have to find the distribution followed by y equals 1 over alpha log of 1 over x, where alpha is a parameter that is greater than equal to 0, right. So, now like we just discussed above, the prescription to convert from one type of random variable to another type of random variable requires knowledge of the inverse function, right, of the transformation, and it also requires the either the PDF or the CDF of the original probability distribution function, right. So, now let us take the original random variable, right, x uniformly distributed between 0 to 1. We know that the PDF probability density function of x, that is simply f of x is 1 if x is between 0 and 1 and it is 0 otherwise. Okay, so, this is already known to us, and we are given that this transformation r of x which converts x to y is simply 1 over alpha times log of 1 over x, right. So, this equals y. So, now that we know y as a function of x, we can find x as a function of y. So, to do that, we simply recognize that log of 1 over x is equal to alpha y, which would mean that 1 over x equals exponential of alpha y. So, that x is equal to e to the minus alpha y, right, and this is basically r inverse of y. Now, if you look at e to the minus alpha y and we are given that alpha is greater than 0, if you plot this, you will see that it looks something like this, right. So, this is a decreasing function, okay. And if you remember what we recently discussed, there is a slightly different prescription which we need to use for when the inverse transformation is a decreasing function, right. So if you recall, what we need to do to find the PDF of the random variable y, that is small g a function of small y, is we need to take minus f of r inverse y, and that has to be multiplied by d dy of r inverse y, okay. Now we know already that r inverse y is e to the minus alpha y. So this becomes minus f of e to the minus alpha y times d dy of e to the minus alpha y, okay. Now you know how to take the derivative of e to the minus alpha y, that is simply minus alpha times e to the minus alpha y times minus f e to the minus alpha y, right. So this simply becomes alpha e to the minus alpha y f of e to the minus alpha y, okay, fair enough. So to proceed forward, we simply have to substitute, right, the value of f here, right, and we know what f is, right. If you remember clearly, f is the probability density function of the uniform distribution. So that is 1 if x is between 0 and 1 and it is 0 otherwise, okay. So therefore f of e to the minus alpha y will be equal to 1 if e to the minus alpha y is between 0 and 1 and it will be 0 otherwise, okay. Now this condition, right, which is written in terms of the exponent of minus alpha y, can be written simply in terms of y. How can you do that? You can take log on both sides. So then the log of 0, right, will be less than equal to minus alpha y will be less than equal to log of 1, right, and I am able to do this because log is a strictly increasing function. So if I take this inequality and simply apply log to every term, then the inequality will be maintained because this is a increasing function. So log of 0 is now minus infinity, so that is less than minus alpha y, and log of 1 is simply 0, right. So what this means is minus infinity is, right, the lower limit of minus alpha y and the upper limit is 0. Now if we multiply the whole equation by minus 1, then we will get infinity greater than alpha y, and that is greater than or equal to 0. And finally, right, because alpha is a positive number, we can divide by alpha throughout and the inequality would not change. Infinity divided by alpha would simply be infinity less than y greater than or equal to 0. So now we have shown that this inequality here 0 lies e to the minus alpha y lies between 0 and 1, that is exactly equivalent to y lying between 0 and infinity, okay. So I hope this makes sense. So going back, you realize that g of y is equal to this, and we have just evaluated what f of e to the minus alpha y is. So therefore we can write that g of y is equal to alpha e to the minus alpha y times f of e to the minus alpha y, which is simply 1 if your y is between 0 and infinity and it is 0 otherwise. And if you multiply this inside, what you will get is g of y equals alpha e to the minus alpha y as long as y is between 0 to infinity and it is 0 otherwise. Okay. If you remember carefully from the previous lecture, this is simply the probability density function of a random variable y that is exponentially distributed. Right. So, this means that y follows the exponential distribution, right, with the rate parameter alpha here. Okay. So, what we have found is actually a way to convert a random number that follows the uniform distribution to a random number that follows the exponential distribution, right. So, essentially what we have done here is we have converted x that was distributed uniformly between 0 and 1 to a random number variable y that is exponentially distributed with the rate parameter alpha, and the only thing we had to do was we had to take x and then apply the function 1 over lambda log of 1 over x, right, and this would give you the desired y, right. So, now if you have a code on the computer that produces a uniformly distributed random number, all you need to do is you need to apply this function on it and you will have a random variable that is exponentially distributed. Okay. So, I hope this example serves to illustrate how we can use these mathematical manipulations to convert a random variable that is sampled from one distribution which is uniform in this case to something that is sampled from another distribution which is exponential in this case, and this can be quite useful when we are trying to analyze random variables and the distributions that they follow, right. So, with that we have actually covered right how we can manipulate probability density functions and cumulative distribution functions and convert them from one form to another. So, with that I would like to end this lecture. In the next lecture we will talk about various properties of a population and of a sample, right. So, usually what you have is you have a large population, however from that population you are only able to sample a few times, right, and from that sample you have to figure out what the properties of the whole population are, right. So, we will discuss various metrics of a population, various metrics of a sample and how these are related to each other, and this will tie back into things later that we do, right. For example, when we do a linear regression fit, when you are trying to fit a linear function to a data, then we get the slope and the intercept, right, and the values of the slope and the intercept will depend on the samples we have taken from the population. So, there will be an error associated with the slope, there will be an error associated with the intercept. So, we should be able to assign things like a confidence interval to the slope and to the intercept, and that is why we are learning all this now. So, thanks for attending and I look forward to seeing you in the next lecture.